So today in class, you guys all made cute little Bohr models of atoms, even though we know that that's not the most accurate representation about where electrons are located. We know they're really located in the cloud. We still use the Bohr model to represent where these electrons are distance-wise from the nucleus. So remember when we were talking about John Dalton, and we said that John Dalton had lots of points to his theory. Number one, everything's made out of tiny indivisible particles called atoms. We know J.J. Thomson shot that one out of the water when he discovered the electron, and we're like, nope, we know that there's something smaller. Then came all kinds of other theories that disproved some of the other parts of John Dalton's theory, one of which is this. There's a part in his theory that says atoms of the same element are identical, which means if I dug a hole in Africa and I dug a hole in Canada and I found some iron, all of those iron atoms from Africa and Canada would look exactly alike. And we're here today to tell you that this is not always true. Absolutely not. So carbon from this side of the world might look different than carbon from this side of the world. And so we're here today to talk about why that's the case and what do we call these weird atoms. So you may have noticed when you were walking around counting protons, neutrons, and electrons and everybody else's atoms, I heard a few people say, oh, they did it wrong. Theirs matched ours. They counted wrong. And in fact, you guys were right on track. So if you look at, this is Miss Dooley's class anyway, our group C and our group D, let's look at what's the same in both of these group letters because there are some differences. So I notice right here, there's one proton. And according to the key over here, there's also one proton. So they have that in common. One proton, one proton. Then I look again, and I look at neutrons. This guy doesn't have any. That's pretty weird. This guy has 1, 2. So atom C has no neutrons. Atom D has 2 neutrons. Then we count electrons. Atom C has 1. So does atom D. So we can put that on our list. 1 electron, 1 electron. So if we look at our list and we try to check out what do these guys really have in common, what we find out is their protons are both the same. Their electrons are both the same. Their neutrons don't match. We have a word for this. The word for this is isotopes. You're going to want to definitely write that down. So isotopes are atoms of the same element. Huge idea here. Same element, but they have different numbers of neutrons. So therefore, their masses are different. So if we go back to this slide and we were trying to identify who is this, here's what you might try. You're going to look at the protons. Since I have 1 proton, I look at the atomic number, and the atomic number with 1 is hydrogen. Hydrogen. So these are both atoms of hydrogen, and we would put a 1 on the bottom. That is the position of the atomic number. Then, if you recall from class, we said we've got to put the mass number in this spot up here. So I say, what is the mass of the hydrogen? Well, the mass of the hydrogen is the mass of whatever's inside this nucleus. Who's in the nucleus? There's 1 proton, 2 neutrons. So he's got a total mass of 3. But check this guy out. He's different over here on the left. He has 1 proton with absolutely no neutrons. So he's only going to have a mass of 1. If you recall from class, we said those electrons are so tiny, their mass does not count. And so therefore, we're going to ditch them from the atomic mass. So the neutrons are different. They definitely affect the mass of the atom, and they have different properties, different forms, different uses. They might even look different to your eyes. One might be purple, one might be pink. They're not the same chemical when you glance at them. So when you're filling out your chart for C, we would have written C had 1 proton, 1 electron, 0 neutrons. His atomic number was 1 because these two guys always match. And his mass number was 1 because mass is a combination of protons plus neutrons equals mass. And then hyphen notation is when you would take the element, I can't fit the name in there, so I'm just going to write the symbol, dash, and his mass, 1. And nuclear notation is when we stack them on top of each other like so. So if I wanted to compare that to atom D, I would say he had 1 proton, 1 electron, but he had 2 neutrons. So his atomic number is still 1. They have that in common. But if I'm trying to find his mass number are the protons plus the neutrons for a total of 3. So this is called hydrogen 3. And it looks like 3 over 1 H. So here are the 3 different forms of hydrogen. We just looked at 2, and you can note what the differences are when you're taking a look at these pictures. They each have 1 proton. They each have 1 electron that you can't see because it's so tiny. And the one on the left has no neutrons, 1 neutron, 2 neutrons. So because there are different forms of hydrogen, we say that he has isotopes. They are all related. They're in the same family. They're just a little bit different. It's kind of like triplets. Even though they all came from the same mom and dad and they all look alike, their DNA's not quite the same, and they have a few differences between them. If you check out this chart, this shows you a few more examples of some isotopes and what's in common and what's not. So check out chlorine. They both have 17 protons. They both have 17 electrons, but indeed, their neutrons are different. So their masses are different here and here, here and here. And then their atomic numbers are still 17. And we should write that 17 on that guy. Same thing with carbon. Protons are the same. Electrons are the same. Neutrons are different, so therefore the masses are different. What do we call these things again? Isotopes. Same element, same protons, different neutrons. Have a great day. Stay tuned for my joke. Have a great day. We'll see you tomorrow.